I'm gonna say that the non-neural network, okay, based, most of them are based on decision tree kind of thing. Okay, the one that you will be using anyway. Now, without giving you anything, I'm just gonna give you what looks like the explanation I showed you earlier, right? If the height is over 1.6 meter, hair is shorter than 3 centimeter, let's call this a boy. Okay, that sort of thing can be generalized to a much more complete algorithm. The most basic, and again, this is the nicest thing, if all the world's classification problem can be answered by decision tree, I would use decision tree all the time. Unfortunately, that's not the case. But if that were the case, it's so nice. It not only gives you the answer, it gives you the reasoning. Let me tell you an example. Okay, and this is a classical example. This is sort of like hello world of machine learning. There's actually iris. Iris is a flower. Happens to have 3 species. Okay, doesn't matter, right? It's it has petal length. Petal is sort of like a petal of a flower, and the other thing is called sepal. Sepal is like a secondary petal. Okay, so these guys have different sizes or length and width of the petal. Also size and width of the sepal. So you have four variable. Okay, so you can call it P length, P width. Okay, you can call it S length, S width. Okay, so basically X1, X2, X3, X4. Okay, now this one happens to be numerical, like in centimeters. Fine. But the answer comes in the form of 0, 1, 2, or in this case, setosa, that's one name, versicolor, virginica. So these are the 3 species. Okay, 3 species. Now, you guys remember this analogy I made about human height, right? Boys have a taller, right? Now, look at this variable. It's called petal width. So that's P width. Okay. And can you see the color? The yellow setosa are skinny, right? And it's so clear cut. It's so clear cut. If you get that skinny, you can make a decision. Now, when you separate the other 2, the blue and the green, it's not so clear cut. It's not so clear cut. But you can still use petal width. Now, this is this example here, you actually use same variable twice, right? In different part of the tree. But in a really bigger tree, maybe, you know, instead of using petal width here, would use length or whatever. Okay, but this example is used because in one dimension, you can do a very good job of separating them in one dimension. What happens if you can imagine that the blue and green sit on top of one another with respect to this dimension? In order to separate, you have to go to another variable, right? So in this case, even though literally how many variables we have in the beginning, I said 4, right? 4. Actually, in this particular problem, because the flowers are so nice, you can just use the width of the petal. That's it. Ignore everything else. Okay, ignore everything else. But you can see that in a general case, you have to search over which variable to look at. Okay, in this case, it happens that, boom, I just told you that, hey, you could just look at petal width and that would do it. That would do it. That's pretty good. Okay, this one get perfect prediction of petal, right? At least for the in sample. This is called in sample result. The other one is maybe a little bit of error, right? predict that it's versicolor, but it's virginica that kind of gets overlapped. But this is already very good. Okay. In real life, you're not going to have that kind of luck. You're going to have more than just 4. Any kind of steps in there. And the first step may be X1. Second step would be with respect to X2 and so forth. So this here is called decision tree based. Okay. Now, why do I say the word based? Because this is 1 tree. It's kind of like upside down tree. It's more like a root. Okay. But we call this a tree in terms of topology. It's a tree. It's kind of branching. Anytime you have a branch, it's a tree. It doesn't have to branch up. It can branch down. Okay. So it's a decision tree. Decision in this case doesn't mean what to do. It's deciding what it is. Okay. Remember English word decide is used twice. One time to decide what to do, the other to decide what it is. I've decided that this guy is a bad person. Okay. You're not doing anything. You just say, hey, this guy's a bad. So that's a classification. So I decide that this flower is setosa. I decide that this flower is versicolor. Okay. So this here is a complete decision tree. 1 tree. 1 tree. Okay. Now, based on this, there are refinement. Instead of having 1 tree, what if you have a whole bunch of trees and you sort of like develop independently and then get some kind of consensus, right? So what do you have when you have more than 1 tree? You have forests, right? So you have things like random forest. Now, I'm just throwing this word out, but it will be in the text. Okay. Sometimes you can take a tree and then you look at the error and then you feed the error to another tree and then you feed the error of that to another tree. So it's kind of like sequential thing. And sometimes that's called like gradient boosting or whatever. So there are many things, but the principle is this kind of thing. This is like condition, and this is very intuitive. Okay. So I am selling decision tree as a favorite. Use it if you can. Use it if it's accurate enough for the purpose. Because if it's accurate enough, it's so pretty. Okay? It's so pretty, easy to explain. Okay? And like Atamfon was asking, why do you prefer a simpler model? It also works when it doesn't work. In other words, when something fails, you can say, oh, you know what? It turns out there's this setosa that has really wide petal or something like that. Okay, so you know where it failed, how it failed exactly. So this is called scrutinizing or scrutineering. Okay, or deep diving. There's no formal word for it. Okay, so you just dig deep into how it works. Remember, I said Basai student should be able to use all the algorithm, knowing how it works under the hood. Well, with neural network, you know how it works under the hood. But when you create the neural network, you don't know how exactly this particular one works. With decision tree, not only do you know how it works in principle, you know how this one in particular works. It works by checking the petal width. Is it greater than 0.8 centimeter or less than 0.8 centimeter? Okay. And if it's greater than or less than 1.75, makes another separation. That's it. Simple as that. Okay. This is called decision tree. Okay. So that's a simple one. Now, let me go to another one. So this is classification, right? So now take out your mathematical notebook and type exactly as I type. Not this one. This one is a little bit too much. Sorry. I will give it to you at the end of the class. Now, this is kind of insight. Okay, guys, watch this. I'm creating a function. Okay? You guys know what e to the x is, right? That's this guy, right? Right? Fine. So what's e to the minus x? You flip it, right? So you get the red one, right? Yeah. Okay. Fine. Now, what else? I can add 1 to it, right? So that's this guy. I just lift it up. So it's a line that goes to infinity to the left and goes down to 1 to the right. Now, what if I take 1 over that? So 1 over 2 is 1/2. 1 over infinity is 0. 1 over 1 is 1. So effectively, I have created this function, this green function. So you see that? E to the x, e to the minus x, 1 plus e to the minus x, 1 over 1 plus e to the minus x. This function here, the green one here, okay, that is part of your life. Now, why is that? It's a function that's non-negative. Okay, so forget all the blue, the red, just look at the green. Look at how pretty it is. Why is it pretty? It's pretty is because it's a value that non-zero, non-negative, can't go negative, right? It's also bounded between 0 and 1. It's also what's called monotonic, meaning that if it increases, it can increase or stay the same, but it can't go down. If it goes down, it can go down, stay the same, but can't go back up. So there's no this, right? If you do this, it's called unimodal. But if you have something like this, it's monotonic. Okay, that's mathematical words I'm throwing at you. Doesn't matter. The point is that it's monotonic. So the more negative the x, the closer to 0. The more positive the x, the closer to 1. But there's a transition. Okay, there's a transition. Now, this function has no parameter. This function has no parameter. Okay. Now, I haven't shown you this. Maybe I can show another one. Yeah, I can do that. Okay. Let me add another one, which is comma. Oops. Comma. Okay. Now, instead of x, okay. Now, instead of x, okay, divide by 0.01. Divide by 0.01. Now, why don't I just multiply by 100? I could, but I'm just being difficult. Where's my mouse? See that? I did a little bit too much. Look, it doesn't have that smoothness anymore. It becomes a step function, right? Actually, if you zoom in enough, it's still smooth. But it gets very sharp, right? It gets so sharp. Okay. This 0.01 here, this 0.01 here is called temperature. Why is it called temperature? Because the lower it is, the more I'm able to freeze the decision boundary. So you don't get to say, is it 0 or 1? Is it 0.6? Is it 0.7? Everything gets pushed. Okay, it's like frozen. Okay, think about it. Think of that green here as a sort of like relaxed. Sometimes I'm close to 1, sometimes I'm close to 0, blah blah blah. But when it's cold, temperature is really cold, I freeze. Now I can either freeze on the side of 1 or freeze on the side of 0. Okay, that's why this parameter, by the way, is called temperature. Now I'm not making this up. It's actually called temperature, and the reason it's called temperature. This is where integrated education comes in. It comes from physics, guys. It's come from Boltzmann temperature. Boltzmann's a physicist. Boltzmann's the reason why you can have an internal combustion engine. One of those guys, anyway. Okay? If you don't have Boltzmann and people like that, you don't have a car. Anyway, it comes from that. It's a temperature. Actually, that's not true. You could, but no. He's one of what's called thermodynamics. Thermodynamics. You should know, right? Okay. So in that case, it's called Boltzmann temperature. Anyway, you don't have to care about that. The point is that I can freeze 1 or 0. Now, what's this function useful for? Well, you guys remember that partition function between red and blue, right? I draw a line that is a curvy line, which is a function of x1 and x2. I put that line in place of x here. And all of a sudden, I've created something that turns a partition line into a partition function between 0 and 1. Okay, let me say that again. I want to separate blue population from red population. What's my job? I draw the line that best separate them. That line is a function of x1 and x2 in this case. I feed that line in here where I see x. And you can see that on the one side, it goes to 1. On the other side, it goes to 0. Okay? And you can imagine that this got to do with neural network. Okay? Ask you this question. Look at this line. This is just a slope. Never mind. Just look at this blue line. What has this line got to do with neural network? Well, I'm sure by now you should know that your brain is not a piece of meat. Okay? It's actually a network of neural cell, neuron. Okay? Neuron or neural cell. Okay? But the real word is just neuron. It's a network of neuron. Each neuron receive stimulus from other neurons. If the accumulated excitation is strong enough, it fires. So you can use this blue function as a model for a neural firing function. And the X here is the strength. If the accumulated signal is strong enough, you get a 1. That's neural firing. If not, you get a 0. And this is a beautiful model of the neuron for one thing. Your brain is not digital. Your brain is analog. Your brain is chemical. You don't get, you have probability thing. It's not yes or no. It's not that precise. It's kind of like, yeah, just about to be 1, most likely 1, but maybe not firing. Okay. So the probability is not that precise. So sometimes having this thing that is not just a sharp step function is very good. Okay. And in fact, you can tune the sharpness. So if I come down here, now this is a little bit detail about, different all kind of function, blah, blah, blah. Whereas the one that say logistic regression. Aha, there you go. Shift enter. Why does your thing hang? Why is it not executing? Yeah, it's been funny. You have a Mathematica in here, right? Don't know why it doesn't shift enter. Why is it gray? Oh boy, that's kind of sad. Anyway, let me show you the picture. What you should get. You should get something that looks like. Okay, let me just go non-interactive. I apologize for this. It should be interactive, but let's go non-interactive. Okay, this is a textbook. It's like one of those things where you always need a. Sorry about that, guys. Ooh. I'll send you a copy of the notebook so you can play with it later tonight. But this is what I want to show. Oh, come on. This is a PDF, guys. It should show up. If you okay, at least it doesn't hang. Okay, if your computer hangs a PDF, then I think you should buy a new one. So what page are we on? I think we are kind of like further down here, I think. Further down, further down, further down. Ah, ah, ah. Okay, well, you should get something like this, okay? It's interactive. It's supposed to be interactive. Oh boy. I think something with your RAM. Okay, here we go. Now, in the interactive version, you can play around with this. Okay. All I want to say is that the same thing I was drawing picture earlier, right? The red and blue. In this case, what I was trying to say is that if you use a thick line, the horizontal line as a separation point, if you skew it a little bit, this is so if you create this kind of surface, so if it's close to 1, you say it is red. Also, in this case, the higher is blue, the low is red. So it's opposite of an example I show you. But that's it. That's it. Now, the thing is, your friends who do logistic regression, chances are they can do this with a straight partition. In other words, the river that separates the two landmass is a canal, is a straight canal. Okay, so that's logistic regression. Okay, now I don't want a straight line. I don't want a straight line. I want a curvy line. I want a curvy line. Now, mathematically, I can do this. I can do what I told you earlier, which is to draw this curvy line as a function of x1 and x2 and put in the x. So that is one. This is, by the way, called transfer function. So you use this function once, but you use it on a complicated river, right? That is the mathematical aim you want to get at, to separate blue from red, when the situation is not simple left and right. However, does your brain work like that? Okay, let me say it again. The red and blue are separated by a curvy line. And you want to create this kind of thing where on the right side of the river, it's 1. The left side of the river is 0. Right? So you go to your friend in statistics. Say, I can do this with logistic regression. Unfortunately, for logistic regression, they can do a canal. They can't do a river. You want a river. Mathematically, you have to create this kind of curvy function. Okay? However, let's try it the other way. What if each one of your neurons acts like one logistic regression? Okay? So what can it do? Canal. But what if you have one canal going this way, you have another canal going this way, and you sum the effect? If you add enough lines, right, you can sort of piece by piece get a curved river, right? If you think about it, a river only looks curved very far back. If you go very close to the river edge, it's actually straight. That's exactly how neural network works. A neural network is a collection of a bunch of logistic regression equations. Now, when I say that a neural network has 5,000 neurons, that's equivalent to 5,000 separate logistic regression equations working together so that they can piece this kind of curvature. Does that make sense? I'm doing the hand waving, but I'll show you it works, really works. But you can see why. If I make one function that looks like this, the other function that looks like this, and I add them together, then it starts to become like a curve, right? Right? That is the power of your brain. Each of your neuron is as smart as a logistic regression, which is not much. But because you have so many of them together, you can add a little bit at a time to get very nonlinear separation. And this can be as sophisticated as you like. Okay? And now, because your brain, each one of your neuron is not connected to just two, right? If you think about it, that logistic regression X1 and X2, that's like saying the neuron feeds from signal from two source, has two input. Well, we can Google this. How many connections does each neuron have? It's thousands. Not two. Not two. So, in other words, you are creating a separation in your brain, not based on X1 and X2, but based on X1, X2, X3, X4, X5, X thousand. When would you need that many? When you look at the picture, your retina is like a computer screen. Each screen has 600 pixels tall, 1,000 pixels wide. That's what? 6 million pixels, right? Right? Each one of those is a signal. So ultimately, your brain can feed off a lot of variable. Even though a single neuron is stupid, and that's why you can drink, right? Because when you drink, you kill some brain cell, you still function. Okay, you can kill 100 brain cells right now. You won't feel the difference because each one is so insignificant. Each one is just a simple, you can lose 100 logistic regression equation, doesn't matter because you have 1 million left. Okay, that's called massive parallelism. Okay, I'm going to show you how this thing works then. I hope your thing doesn't fail me. But anyway, in details, I'm going to actually have one class devoted to decision tree like, but not only am I going to make your life easy working with Mathematica, I'm going to make your life hard by having you work with decision tree on Python platform. Reason being, it's very ubiquitous. So if you get a job, chances are, because Python is free, right? Any startup is going to have Python library in the workstation. It's free. Okay, you don't have to pay any money, so zero capital. So chances are, wherever you go, at the very least, if you can't play with decision tree on a Python, then you make us look bad. You make us. It's one of those things like like a basket analysis where it's not that complicated, but if you don't know it, you make Jula look bad. Okay, so either next week or the week after, I will have Kong Kan come and run you through that. Anyway, so today I want to do something different. I want to say working with supervised machine learning. Okay, hopefully your thing works. Now, let me. Okay, I'll go through step by step. Okay, ideally you would be typing along, but if you can't, it's okay because okay. So first of all, financial data is a function that calls on a curated database within Mathematica ecosystem. Okay, so this thing is quite easy, but alternatively you can go to Bloomberg, download, Writer, whatever, it's okay. But this is what I did. Basically, I just load financial data, dollar baht, right? That's the currency. From this example, I just 2020 because I think I wrote in 2020. So I did that. Don't tell me it's not running. I think there's something wrong with your configuration. Okay, let's pretend that we are running this live, okay? Hey. Okay. Okay, so basically, same screen, except this is actually PDF, embarrassingly. So I download this data. I take, the rate, what the value is. It's, 260 days, fine. And I take, so length of, I name this thing, okay? So basically, FX data is this thing, right? But it has dates, it has value. I just want the value, okay? I'm just making life simple. So the value is FX data, and this is like a data frame, right? Just put in the name value. So basically, this is a data frame. So value, I just happen to know it's called value, but you can list the head. So that becomes rate, okay? Now, I take FX rate, I look at the first three of them. I also want the length. So 260, that's normal, right? In a typical year, you don't have 365-day trading. You have about 252 or 260 days. So that's the first day, second day, third day. So 29 baht to $1, 30.15 and 30.15, whatever. Okay, fine. Now this is how we work with this. Okay, I'm not going into the actual individual model, but I just want to quickly take you through what's called a pipeline. So what you do? Well, first of all, remember I told you that you want to learn about interpolation and extrapolation. You don't want to just be able to fit the data that you can see. Okay, so what you want to do is fit the data you can see, but then test on the data you cannot see. Now, what data scientists do then is that, well, I see the whole 260 days. I'm going to pretend I don't see part of them. I block that out. So this is where I use the take drop. Okay, so there's a train set and there's a test set. Okay, train set is equal to take drop, right? And basically, floor is round down, 0.75 the length of FX rate. In other words, I take 75% of the series as a train and 25% as a series for a test. Okay, now, one point to note here. This thing is a time series, so that the first 75% is older than the last 25%. What this means is that I will be training my model on the longer history and testing it on a more recent history. Okay. Now, sometimes you don't want to do that. Sometimes you want to train on the recent history, test on the further back, or sometimes you might want to do sort of like partition and move things around, kind of randomize a little bit. But for simplification, I'm just doing this. Okay. So basically, the first 9 months I use as training, and the last 3 months I use as testing. Okay. Now this here just looking at the end date doesn't matter. Now, to be honest with you, predicting FX is really easy. Okay, this is probably 99% accurate right now. I tell you what's not easy: daily change. Okay, and just to make life difficult, instead of FX rate, I do FX return. So basically, I take the log of 1 day divided by the previous day. Okay, this step you may not understand. That's okay, but basically, I just want to make your life tougher. Okay, predicting FX rate is easy. Predicting 29, 30, that's easy. Predicting whether or not there's going to be a change in many percentage from day to day, that's hard. Okay, so I did that. Right. So I have FX rate train, okay, and return. So this one I'm going to use. FX rate is just the beginning. Fine. What I'm going to do here now is to make y as a function of x. But I only have one thing, which is FX rate. So what is the y? What's the x? The x is previous, say, 10 days of x of return. So use the 10 days to predict the 11th day. That's what I mean. So the 10 days are my x's, And the 11th day, that's my Y. Okay? สอนสี่ครับ So 10 days of return, my X, the 11th day of returns, my Y. That's basically what this does. Okay? Okay. สอนหนังสือครับ 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 Okay. Now, that's one data set. Okay? It's one data set. That one is obviously what kind of problem? My output is numerical value. It is a regression or prediction problem, right? So while I'm doing that, I'm going to do another data set. This data set is actually the one that we saw earlier from the flower, right? So this is Fisher Irish. Fisher, I think, is the name of the person who kept this data set. And Iris, Iris is the name of the flowers, okay? So this is actually a measurement of 150 flowers in 3 species, 50 of each. 50 of each, okay? So the first 50 is one species, the second 50 is another species, the third species is another 50. So what I have to do now, because I want to make a classification problem, right? I have to mix them around. So that's why there's this thing called random sample. So I mix them about. In this case now, it's not the first, you know, so I mix them, right? Now, so you see this arrow here? This is kind of like the association thread, but it's easier to see from this example. Now, in this case, instead of making input and out, in the previous case, right, I separate training set and testing set, and then I turn that into return, then I turn it into X and Y, right? In this case, I make an X and Y pair first because there's no order, there's no time order. Okay, I already mixed it up. So what I do here is here, yeah, thread or association thread. So what I do is the first 4 numbers are the sepal length, sepal width, petal length, and petal width. Okay, and the 5th number is the label. The label. Okay, so I make the thread between so I have a list of 4 number and a list of 1 number, and I thread them so that the first 4 point to this one, the second 4 point to the second one, the third 4 point to the third one, and so on down the line. So now it becomes what I call IO data. How does it look? See? So the 4 measurement point to name, 4 measurement point to name, 4 measurement point to name. This is called prepping the data. Okay. So anyway, so I have that. Okay, so I prepare 2 data set. Okay. Okay. I don't use the FX rate. I use return, and I use the flower. Okay. And for each of them, I have training set and testing set, each of which is a series of pair from input to output, right? And this is where I think P. Gongkan, your TA, has shown you, like, you know, formulation with Python in a collab. But, you know, that takes a tremendously long time. So all I have to do is this, guys. Okay. This is my prediction. Predictor is equal to predict this data set. That's all, 1 line. Now, I actually make 2 separate versions. Okay. Right? This predictor, again, if this were a mathematical notebook, you can press F1 and go to the help desk, right? It's going to give you, what does it do? It's a constructor function. It gives you a function. It doesn't give you a number. That function is your predictor. Basically, you're building the model. This model is constructed using the return data that comes in an IO pair, right? Input and output, 10 days, predict 1 day. 10 days, predict 1 day. And What data set am I using? Train. So that I don't see the test set. I pretend I don't see it. Now, this would work for a small data set because effectively Mathematica is going to try a bunch of methods. In a real life application where you start working with real model, you would have an idea of what model you want to pursue. Let's say I've done all that work and I've decided the best tools I'm going to use is called neural network. Okay, a neural network is like many logistic regression. This is how I would do it. Okay, so whereas with Python, you would actually download different model. Here you just say create a model and you specify as an option. I want to use this method, neural network. Okay, now, again, so I create two predictor. One predictor, I don't specify the type. Mathematica tries a whole bunch of them. It turns out it likes random forest best. Random forest, by the way, is a bunch of decision tree. Just came up with that because it thinks, okay? Whereas if I specify it's neural network, obviously it's a neural network. The function to use is called predict. Predict, construct, prediction model, or regression, so to speak, okay? So the other problem, the iris problem, I'm not going to use predictor, right? I'm going to create a classifier. So the function I use is classify. The function say classify, but what it returns is not classification, but a function that does the classification. So now I don't specify it. It comes up with, okay, actually, if you double click plus, it's going to tell you what method it uses. Now, the second line, let's say I prefer to use decision tree. Same thing. I specify the method. The method is decision tree. Okay. So the second one here, if I double click down here, I'm sure it's going to say the method is equal decision tree. The first one, I don't know. Okay. This is a PDF, so I can't double click. Right. That's it. You don't need one page to build a model. Okay. You don't need to import scikit-learn. You just say predict. Now, obviously, Mathematica is more powerful than that. So there's an optionality that you can dig into. But this is all like the first pass for a small data set you can do. This one, I like to do this. I put timing in front so that it say how many seconds it takes to do it. Okay, because I like to keep track of how fast, how slow my computer is. If your thing works, and this maybe take 5 minutes, I'm just making fun of you. But this is 0.7 of a second. This is 0.125 second. Okay. Now, once I've got a model, okay. So the pipeline here is prep the data. Basically, there are two things you need to do: make it into input-output form, row of input and output. Pair, right? So input with an arrow, output, input, out, arrow, output. Input can be a whole bunch of numbers. Output has to be just one thing. And that one thing can be number or just label, because Mathematica understand nominal scale. So you don't have to say Sentosa is 0. It knows that, yeah, okay, implicitly you want to do that. So that's kind of like housekeeping, but internally there's a 0, 1, 2. Anyway, so you build it, okay? You separate training from test data. You train it on the test data. You train it on the training data. Now, this is why I want to be brief, because I want to, we're doing pretty good on time, actually. I don't have to be brief. So let's go to the first one. Once you get the model, you want to know how well it's doing. Actually, by training the model, the algorithm already knows how it's doing with respect to the training test. Because after all, it's trying to minimize that error. But you want to test on the unseen data as well. Now, technically, well, you're not required by law to report the performance of the training on the training, because that's kind of like back end. That's what you do. You're supposed to report the result of the testing on the unseen data. But as a developer, and this is a skill as a developer, you always test even for in sample, because you want to know if the performance deteriorate a lot. Do you know what I mean? Okay. So if you train model on the what's called in sample, you can't show performance on the in sample and say you did a good job. That's cheating. So when you show the result to the publication, to the client, to the research forum and seminar, you have to show the result of your model on unseen data. Okay. But while you're developing the model, you also want to see the performance on the training so that you know that, hey, the performance is good here, but it drops severely here. So that means it doesn't generalize well, for example. In a time series case, this could be simply because the last 3 months of 2020 is very different from the first 9 months. Could be. Okay. So you do this kind of analysis and then you switch around. This is not one shot, by the way. You keep going back and forth. Maybe you put the training set here, put the training set in the beginning, the test set here. You try to find out what happened. Okay. So there's more to being a data scientist than just running one line code. But, you know, hopefully with one line code, you don't have to run the whole page. That's good enough. Okay. So what you have to do is look how well you did. Now, if you go to regression equation, what is the performance statistic? You have R square, you have maybe some kind of test statistic on significance of the coefficient and so forth, right? That's very model independent, right? Here, I'm going to give you the generic performance measures for classification problem and for prediction problem. Okay, so let's start with prediction problem. Okay, prediction problem. Now, the way to do it, okay, let's go to the first one. So this again, you double click this, you should get that. Just as you use predict to construct a predictor function, I use a function called predictor measurement to get all kind of performance statistics. Okay. In fact, when you do that, it gets all possible performance statistics, not just R square. Okay. Gets whatever is available. You can look at the, you know, and so what I do is, okay, this one here. Okay. This is the function called predictor measurement. Again, it gathers statistics. It tests predictor, this guy. You remember this one, what that is? That's the one that I didn't specify the method. So it came up with what again? Random forest, right? So this is the random forest on the training data in sample. This is the performance of a random forest on the testing data that's out of sample. This is the specified neural network in sample, out sample. So it gathers all kinds of performance statistics. Now, by default, if you don't say anything, it's going to give you this set of statistics. So what it means is that for most professional, these are the things you want to look at. Standard deviation of baseline, R square, mean cross entropy, single evaluation, and you need that. Basically, this is the R squares, okay? And they plot this as well. This is actually actual versus predicted. Now, the left-hand side is in sample. The right-hand side is out sample. They're both not very good. Why? Because look at this. The actual value, you know, go from -0.5 to +1, but the predicted value is just, in other words, it's kind of predicting the average. This model is not very good. Okay? It's not very good. We haven't fine-tuned anything. This is kind of like first pass. This is kind of like, you know, starter kit kind of thing. Okay. Right. And predicted values like that. Now, see if neural network does any better. It's not going to do any better. Okay. It gives more spread, and there's a little bit of ideally, what you want to see is thing on the 45-degree line, right? You see this 45-degree line? Yeah. What's a perfect prediction? Perfect prediction is whatever the predicted value is, actual value is, the predicted value is the same. So everything on the 45-degree line. It's not quite. It does get some, but not really. It's still a terrible model. Okay. Sorry, this is actually not 5 micro. This is 5 watts. This actually burns paper. So I use this because I was making a presentation of big auditorium. This was back when I was talking about quantum computing at SCB, and we have the huge hall. And then, so 5 watt is going to burn your eyes out, by the way. It's not a toy. Yeah, sorry about that. I should get a 5 microwatts. So you can see that it's not very good. This is it. This is what's called standard performance report. Now, there are actually many of them. So if I take the predictor object here and I say properties, these are all the information you can have. You can have batch evaluation, log likelihood, prediction function, residual histogram, residual plot, baseline, total square, Sharp plot. Sharp plot, by the way, is something that is very good. Okay. Yeah. This is something that that I'm going to have you go through. I'm going to have P. Gongkan, your TA, show you this, but he's going to show you using Python library. So it's going to take a bit more steps. The reason I want you to do that is because the Sharp library in Python is also one of those things that's used everywhere. So if you graduate and you don't know how to use it, you make your look bad. It's one of those things. Okay. So anyway, so there's so many things. Now, let's go look at this. For classification. Now, again, it's not getting value, right? It's getting individual class. So it's called, the function is called classifier measurement. Okay? The function is called classifier measurement. Okay? And, there's a difference. This problem is much easier. Look at the accuracy, guys. Holy cow, 99%. So this is a baby problem. I show you 2 extreme cases. The first one, essentially, you're trying to fit noise. So the first pass is not, it's going to be like incredibly powerful model that can predict noise. It's really that difficult. Okay. This one is trivial. Okay. And why isn't it trivial? You saw earlier, right? I just look at petal width. If it's below 0.8, I get perfect prediction every time. Okay, so I know that this one is the opposite case. I'm demonstrating the opposite case, not just different technique. So this one is like that residual plot, except it's called confusion matrix. It says how confused the model is. The actual on the left, predicted on the right. In this case, you also want 45-degree line, but it's kind of diagonal the other way, right? So out of 38 setosa, 38 setosa. So this one making, how many errors is it making, guys? 0. In sample. Now, out sample, it makes 3 errors. And if you think about it, that kind of looks like what we saw earlier, right? Virginica and versicolor. So anyway, what this means is that there are 3 versicolor actual case, actually versicolor, but the model say Virginica. So out of 112, it makes 3 errors. I don't know what this is, but this one I know it's a decision tree. It's also kind of make 1 error here in sample. It makes 3 errors here. So just as good. Okay. Again, so many things. And in this case, log likelihood, misclassify, all kind of stuff. But now, okay, very good, very good. We're doing very good on time. We can go talk about the project, but I don't want to go yet. I want to talk about this, and then we are done. This is going to be part of the textbook. It's going to be it's not going to be part of your thing except 3.1. Okay. So 3.1 is a neural network. We'll go into details later. So right now, in terms of supervised learning, what do you know? You know that there are decision tree based kind of techniques, right? There's neural network based technique. By the way, there's another thing that's even simpler. It's called nearest neighbor. That's like saying, I want to see what the boy, if it's a boy, if it's a girl. Well, look at the previous people. Who does this person match in terms of height and length of hair? The one who matches the most happens to be a girl, then you say it's a girl. If the one that you match the most is a boy, you say it's a boy. Now, you don't say the nearest match. Maybe you take the nearest 5 matches and average out. Okay. So these are called nearest neighbor. Okay. There are little techniques here and there. But essentially, if you know how decision tree works, you know how neural network works, you might need to know a little bit more about architecture than what I show you today. You're good, at least for data analytics. Now, before I go and talk about the project, I want to dwell a little bit on this kind of thing. Again, there are models that works, and you know how and why it works, right? Things like decision tree. Well, not only does decision tree works the way you understand it, so does linear regression, right? You actually can, I don't know how much of linear regression you've done, but you can do estimate on the significance of each beta, right? Do t-test, S stat, whatever, all kind of stuff, okay? Those are algorithm specific. So if you work with linear regression, you can do this, t-test or whatever, significant of each component. If you do decision tree, you also have that diagram, very pretty diagram that I showed you earlier, okay? By the way, the real diagram is not just 2-layer. It may look like this, okay? By the way, this is a complete diagram for the same problem, okay? Just separating also 3 colors. So again, that's setosa. That's easy to separate. The other one are more difficult to separate, so you actually separate a lot more. Okay, what you saw before was just this 2 chunk. Okay, I show you a nice picture that's just here, but actually in reality, you can do more fine tuning. So this is actually what an actual tree looks like. Okay, so you have to depends on I guess visualization software to draw that. Okay, and again, it's specific to decision tree. I think this one is graph viz or something, whereas this one is this one is called dviz3 or something. Oops. D3viz or something. Okay. Anyway, they both are available on Python. They work off result from scikit-learn. So พี่กองการ UTA is going to come and take you through the collab sheet. Okay. Anyway, so again, see, 1 branch, 2 branch. So these are the 1 branch, 2 branch, but real solution go further down. So that's what I call algorithm specific. Okay, I give 2 examples. So fitted regression coefficient, you can do that. Decision tree parameter, you can do that. Then you have what's called algorithm agnostic. This would mean something like, what if I don't know what the underlying model is? Can I still guess how it works? Think of how difficult that is. Neural network has 50,000 parameters. You don't know what it's doing to each variable, but I'm trying to sort of like get a feel. So how would I do that? How do you think we can do that? This is not about measuring the performance, guys. This is about saying if the model is not transparent, it's not like, height greater than 1.6, hair length less than 3 centimeter, but a whole bunch of function like this, 1,000 of them. I'm trying to understand the reasoning. Okay? How would you do that? Okay? How would you do that? Well, you can do, one of the things you can do is come up with a test case. Hey, you know what? There is this guy, this person come in, he's 2 meters tall, and the hair is 12 inches. Who do you think it is, a boy or girl? Okay. Now you're giving an extreme case for both, right? Hair length, and let's say it turns out that someone very tall, long hair, and the model say it's a boy. What can you tell about that model? That model pays attention to height, not so much on hair length, right? So you can kind of like give it extreme case. Okay, but extreme case has a problem. One, it's not realistic. Two, the model shouldn't do well anyway because you are actually, it's like you're learning about human being and you're giving an alien population to test. That's not valid, right? The test should be based on the sample you haven't seen from the same population. Okay? What if there's no 5 meters tall, foot long hair human being, and you use that as an extreme case? Are you going to get any insight? No, you're not, right? So the best thing is to actually use the data itself, like the training data or the testing data. Doesn't matter. In fact, in this case, you would use the training data because it's working on the training data. So you want to know what things, what aspect about the data gives you that. And what you can do is this thing called SHAP analysis. And this is a prelude. I'm just going to give you, maybe I give you some reading or, your TA. But basically, SHAP, by the way, doesn't come from data science. SHAP comes from Shapley, name of the person. He's a game theorist. You know what a game theory is? Game theory is fairly advanced mathematics. Things like you have a team, and this team does well. Okay, fine. The team does well. I want to know how much of an individual contribution this person made. Okay, so if you have like a team of 5, okay, and that's a whole bunch of hackathons, okay, and sometimes you have this person, sometimes you don't have that person, and sometimes with this person you win, with this person you lose, or something like that, that kind of thing. And you try to sort of like extract, hey, what if I kill this guy? How worse off would the team be? Okay, it's that kind of thing, that kind of individual contribution. Well, for each input xi from x1 or x2, you can do that kind of thing. You can say that because the value of this xi for this data point, I predict a boy. The model is looking at this guy's height and say it's a boy. You see what I mean? It's this kind of analysis, like individual contribution of a single variable to a prediction of each prediction. Okay? Each variable's contribution to each prediction. And then you can do some kind of, it tends to be the height, the taller the guy is. Let's say you don't know that what the model is, but you did this, you come up with the conclusion that, you know what, the taller the guy is, the taller the person is, the more likely it's going to be a guy. And the sort of like midpoint between boy and girl tend to be around 1.58, 1.62, that sort of thing, right? And also, hair length seems to matter. Seems like a short hair tends to push toward a girl. And the cutting off point is around 2 centimeter, 3 centimeter, 4 centimeter, that sort of thing, right? So you can imagine that without opening the guts of the model, you can sort of like test and get a rough idea, okay? Now, why is this tool good and why is it dangerous? You know what it's good for? It's good for developing model. Because you know what that direction, you know what kind of variable means a lot. And sometimes you can see that out of the 200 variables, only 12 of them are doing the pushing, for example. Okay? Why is it dangerous? Well, imagine this is a loan approval, good credit, bad credit. And you do this and you publish it online. Now, what's going to happen to the loan applicant? He's going to game this thing, right? He's going to say, oh, which one pushed to the right-hand side? I'm going to lie on that one. Okay? So you can use it to game the input. Yeah, so that's no good. So that's the danger. But this kind of understanding the model indirectly, which is called algorithm or model agnostic. Yeah, I might change it to the word model agnostic because it's not just algorithm. So method specific or agnostic. This is very important. And you're going to learn that skill. And because decision tree and SHAP analysis are so ubiquitous, as is Python, it's not good enough for you to just take it easy and use Mathematica, right? I'm going to have you guys go to the code lab. It may take 50 more lines, but hey, that's life. Okay? And Gongkan is going to take you through that. He has the patience. I don't have that patience. Okay. Yep, that's about it, I think, for today. Now, next week, one or two things happen. Either Gongkan come in and take you through this, or I might do what I do today for unsupervised learning and then stack P. Gongkan's exercise later. Okay, let me work with him. He's quite busy as well, so sometimes I have to. He's the one who's busy, not me. Okay, but he's very, very good. He's very patient. Okay, so the boring stuff I give it to him. And right now, let's go to what I want you guys to do as a project. Okay. For uniformity, some of you may be actually better off with Python, but I would really prefer if you do this within here. I'll show you why. One of the reasons is, yes, you can get away with quote unquote pitching. Okay. And that's what Basai students are very good. You guys are good at making pitching deck. Okay. Sometimes I think Basai should stand for best pitching deck school in whatever. Okay. But sometimes you should do more than that. And professionally, you don't just do pitching deck. Okay. That's for sales. But legally, you also have to do technical documentation. Okay. You can't, I have to do technical documentation when I develop because what I'm handing over, I present the paper to people who pay. So I use pitching deck and delivery deck. Okay. But the project is only signed off if their technical people can take over the technical codes. So there has to be what's called, sometimes I just call it white paper. Okay, it's basically technical documentation. That is something that unfortunately is underemphasized in Basai. So I'm going to emphasize it here. Your project will have everything. It will have, because I know you like to make video, TikTok video, you're going to have video presentation of your project. Okay. Although I would prefer this way rather than TikTok format because, okay, I don't want to look at this with the blurry thing on the side for 3 minutes. Okay, it's not a TikTok thing. So, but be brief. So you can have to have a video. You can have a presentation deck, but you also will have a technical documentation. Now, if, and this is how you do it professionally, your platform depends on what your client use. So if your client use JavaScript, you have to write JavaScript. Your technical document will be in Word. Okay, and what you do is you clip some screenshot over here and you paste it, and you take another screenshot and you paste it, and take another screenshot and you paste it. It's the way I would write textbook as well. Okay, normally most people write textbook that way. Okay, but with Mathematica Notebook, you can do one thing. So your calculation and documentation is the same page. Now let's see. I hope you don't embarrass me with your thing. Now here, let's say, well, we can do new. And by the way, do you know what LaTeX is? For those of you who want to go into more professional and even academic career, you have to learn what's called LaTeX. What it means is that it's completely format free. Okay, but every text has a function. This one's a heading, this one's a subheading, this one is a pointer, this one's an explanation, this one's a table. Depending on how you want to look at, like, it could be in Times New Roman, it could be in Sarabun, it could be 12 point, 30 point. These are parameters. You specify that heading has Times New Roman, boldface, 34 point. Okay, and you run that and you get it. Same text, if you say, well, I want it to be Cordial New 12 point in blue, you get that as well. So in the same kind of spirit, check with your, okay, try to run the, so let's say, remember I told you that here, go down here, right? Text. Now you can have plain text, hello, okay, but you can also have other type of text, like title. Say something like item, okay? Author, okay? So author, so okay, that's not very different. So let's try again. Let's call it, where's the title? Title is T, right? How come that, why does it not scroll? Okay, let's say subtitle. Okay, right? Now, this is not format free because it comes with the default format. But what it means is that you can go here. Keep forgetting. Style sheet, I think. There it is. Style sheet to chooser. Okay. So if I did this, it becomes this format, right? Same text, right? If I go to so here, format, style sheet chooser, then it looks like this. Okay. Now this is what I want you to do your final paper in. Now, I guess I'll give you a freedom to choose style sheet. By the way, the style sheet can also be customized, but I don't want you to waste time doing that. Okay, so something like this. Okay, so in fact, if you think about it, this notebook that I'm using to write the text, I'm using, I think, this style sheet. That's why the author name is in blue. Okay, that sort of thing. Now, and equation. Basically, at the bottom end, it should look a little bit like manipulate this. Okay. That should be at some point your application end. So there should be manipulate and something, 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 and something, something, something. Okay? Data analytics. It could be, again, based on visualization. It could be, that sort of thing. So you're going to have this quote unquote interactive visualization at the end, regardless of whether or not your thing is based on interactive visualization alone, based on statistical probabilistic models, or based on machine learning algorithm run on data. Okay. Now, what I like to do is to make sure that, are you guys sitting by groups? Ah, good. So I'm not going to save anything. Okay. So let me bring up a little. Maybe we can just bring up sort of like a worksheet, maybe. Start an Excel or something. Okay. So now you fine tune this later, okay? But basically, I obviously need to have a name of the team and the suspicious. Okay. Right. So, for example, let's run down quickly. What's your name? What's your team? Team's name. Okay. Team 1. Hey, what happened here? Get a lot of, okay. So let's say team 1. Okay. Whatever. Okay. So team. Now, and then what's area, data set, and so forth. This you can do later. We don't have to do it now. But what I want to do now is to make sure that you don't get too trivial for data set. You can be lazy and work from Mathematica's data set because it's curated. But it would be maybe even nicer if you go to, say, Kaggle, you go to GitHub, you go to actual, if you want to work with temperature reading, ice core reading, you actually reference external source. And you remember that in Mathematica, you can import open bracket, HTTPS, semicolon, and so forth, right? You can literally import that. If it takes a long time, you import it once, save it locally, and then just read it from file. Okay. Now, how many team have we got? So 1 team, raise your hand. 2 team. 2. Okay. 3, right? Okay. So what's your data set? Now, actually, this is a wrong way of saying, you don't say, sometimes you begin with technique motivation. Like when I'm doing research, I want to do graph theoretic analysis. So I look for data set that has a graph structure. But I start with the technique. That's my motivation. Sometimes I'm giving a really good data set, say medical imaging, and I look for techniques to apply. Sometimes I'm given a problem. I haven't got the technique. So it's always technique, data, problem. Okay. It's sort of like, sometimes you have freedom to choose. Let's put it this way. Okay. If you're a professional data scientist, you don't get to choose problem because you are paid to do this problem. For example, if you're an academic and you want to say, hey, I'm an academic, I want to write a paper on graph neural network. I'm just looking for data that has a graph structure. Okay. So you don't have to say, start with data. You can start with technique. You can start with problem. Okay. So one of those things has to be your your flag, your target. Okay, what are you aiming for? First of all, are you aiming for data, problem, or technique? Okay, let's make life easier. Okay, everybody think of yourself. What motivates you? Okay, what's your lead line number one? We are going to work with this technique. We're going to work on this data. We're going to work to solve this problem. Okay, problem, data, technique. Let's make life simple. Okay, what motivates you? Getting good grades? No. Okay, I'll skip you for now. No, not TikTok. Data, problem, or technique. What? Okay, that might work. You're gonna have to be more specific than that. You want to find out how it works? Okay, let me come back to you, but this is interesting. This is not a data analytics project per se, as it is more like reverse engineering. Is it doable? Yes. Can you formulate it as a data analytics problem? Yes, but I suspect you're going to have problem with getting the data to work on. Because you are not going to have access to TikTok's recommendation record. So you don't know what their X and Y is, but you know that there's an algorithm in there that takes an X, like input and Y, and maybe you want to do exactly what I was just telling you earlier, do some kind of Shapley analysis. The point is, if you work for TikTok, fine. If you don't work for TikTok, you only get your Y as a function of your X. You're not going to be able to do data analytics there. So I really think you're going to have a tough time. So I have to think of something else. You see what I mean? It's not a bad thing. If you are a consumer advocate groups and you have 1,000 people who's willing to record what they put into TikTok and what TikTok feeds them, give it to you. Maybe somebody has done this. I don't know. TikTok IO, TikTok recommendation history. Okay. And you can reverse engineer because you want to work out whether or not TikTok knows about my age, for example. Okay. Yeah, that's going to be hard. I'm not putting that down yet. I think of something else. Or yeah. Next, to your right, there. Guys. Yep. You have no idea. Okay, who's your group? Who's your team? He hasn't got a team. Ah, okay. Who wants him? Or you can do solo if you want. Okay, but still have to have an idea. What do you want to work on? I'll come back to you. Okay, you. Sorry? Medical record would be good. I would love for you who work on medical records. I did, by the way, remember I told you about consultancy job? I do consultancy job before, obviously, still open to it. There's some problem that turns out that advanced techniques yield as much of a good, as well as decision tree. Exactly the thing I was telling you about, okay? So what happened? I was motivated to use decision tree for that solution. Okay. So in fact, we used listen, except by the way, it's not that the tree looks huge. It's like a huge tree. Okay. Because we got so many variables. Okay. It wouldn't fit in a page. But based on that, Based on that, let me go to internet. Where's internet here? Yeah. Based on that, I got to improve. I improved the basic decision tree with what's called fuzzy score. Okay, fuzzy set theory is something else that you don't have to know. But let's say now, so this is the technique I developed. Obviously, I can't publish my client's data, right? So what I did was I went to medical data, breast cancer, Wisconsin, I think probably Wisconsin hospital or something like that. So they have a breast cancer Wisconsin diagnostic data set from the UCI machine learning report. By the way, this is also another thing. Besides Kaggle, this is very good. Okay. In fact, I just shopped around for that. And the paper, so the code is here. The code is here. That again, that's Gongkan. That's your TA. He wrote the codes. And let me see what the medical. Yep. Okay, so that's me. That's Gongkan. That's the algorithm, and this is the improvement on it. But we have to go. Okay, so this is the data set. Well, it's in here. The data sets, it's referenced here. So yeah, medical data is very good. This one is diagnostic. What it means is that you are classifying yes or no, or cancer or no cancer. Okay, so sometimes you detect a lesion, and sometimes in medical diagnostic there are two kind of approach. One is to actually use the direct imaging. So let's say a scan of a breast, X-ray. Okay, if you scan the breast and you see black dot or whatever, I don't know what it is, right? And then you use CNN and then identify. So that would be like image classification. But if this thing gets on record and somebody digitize it, measure the length of the lesion, measure the whatever, it becomes a number. Okay, like length of the black patch or the location of black patch relative to the center of mass. I don't know. Okay, and some kind of blood testing, some reading. So these are numerical, right? If you record this as a table, then it becomes prediction problem, just like we saw before. Okay, so medical diagnostic tend to have, right now anyway, direct sensor or imaging to diagnosis or numerical indicator. Okay, numerical indicator. So yeah, that would probably work better than TikTok. Okay, behind you. Okay, let's make this a homework then, because you guys are not prepared to talk about anything, and I don't have anything to talk, so maybe we'll leave early. No, I leave early. You don't leave early. You sit around, you work on it. Make sure they don't leave. We'll lock the door. Okay, work on this. Again, you can be motivated on data, technique, or problem. I recommend you guys have internet right now, correct? Okay, so go to this guy. Go to this guy. Okay, go to this guy, for example. Okay, machine learning repository. Now, this is one. The other one's Kaggle. The other one is go inside Mathematica if you're that lazy. Okay, and do data object. There's huge data there. So yeah, if you go to that, then you obviously have to work hard on the technique because data is easy to find. Okay, so why don't we do that? Good, because for some reason I'm running out of voice today. I'm not okay. So why don't you guys sit around in groups? Okay, don't leave. Okay, and work on your group or your team. The single guy, you can work singly or you can find friends. Okay, it's okay. It's, you know, I'm a loner as well. I don't. Okay, but what I want as a homework for, shall we make it tonight? Okay, tonight, 5 items. 5 items. Number 1, your team. Okay, who you are, whatever, student ID, blah, blah, blah. So that's that. Maybe you give it a name. I don't care. Yeah, just give it a name. Number 1. Number 2, are you focusing on A, B, or C, right? Problem, data, or technique? Okay. 3, go into it. Okay. Data, I want to work with medical data. Technique, I'm going to try. Now, this is a little bit tricky if you go for technique because you haven't learned unsupervised learning. But basically, unsupervised, remember that group, that labeling blue and red? Now, what if you are not given blue and red? And you want to know if they're actually different faction. Okay? So is everybody homogeneous or is there a faction? So something like that would be unsupervised because I don't have the right answer. I just see a whole bunch of data, but based on this, it looks like there's a cluster here, there's a cluster there. So this sort of thing are kind of like characteristic of the data that you can make insight from. Now, once I teach you unsupervised learning, maybe I should teach you unsupervised learning first. Once you learn unsupervised learning and supervised learning, you realize that some projects feed off of one another. In other words, instead of giving X to predict Y, you do cluster analysis first, and then use the cluster name to make prediction. Well, you know, that sort of thing. There's so many ways that things can lay on top of another. So this is a little bit more of a professional thing that you mix and match techniques. But try to as much as you can. Tonight is just an exercise. You can change your mind. You don't have to keep to the same thing. But let's say I say you have to say 5 things: who you are, what you're focusing on, data, problem, or technique. What is that? Okay. Then the 4th one is you sort of like game plan. Like use this to do that so that I can visualize. And finally, the 5th one is link all the resources, whether it's URL, whether it's textbook, whether it's UCI, whether it is Kaggle. Okay, so all the links. Okay, 5 things. Okay, so you can use that, play with that, and let's make it. Or you want to make it end of class exercise? Tonight? Okay. So 8 o'clock tonight. Okay. So you make the my course view spot for it.